In environments where performance improves with use, like training a neural network, tuning hyperparameters, or teaching a robot a new skill, the optimal strategy isn't fixed. It changes depending on how much time you have. This is the core idea behind the rising multi-armed bandit, RMAB, framework. Unlike standard bandits where rewards stay constant, in RMAB, each arm's expected reward increases with the number of times it's pulled. Think of it as gaining mastery through repetition. The more you train a model or practice a skill, the better it gets. But here's the twist. The optimal strategy depends critically on the time horizon. If you only have a short time, you're better off sticking with an arm that already performs well, what we call an early peaker. But if you have a long horizon, you should invest in an arm with lower initial reward but higher growth potential, the late bloomer. This phenomenon is known as horizon-dependent optimality. And yet, most existing algorithms ignore this crucial fact. They're horizon agnostic, meaning they don't know how much time they have, so they can't adapt their strategy accordingly. The result? In short horizons, they waste time chasing high-growth arms that haven't had time to pay off. In long horizons, they cling to early peaks and miss the real potential of late bloomers. So how do we fix this? We introduce CURE-UCB, a novel algorithm that explicitly leverages the known horizon to make smarter decisions. Instead of estimating instantaneous rewards or growth rates, CURE-UCB estimates the cumulative reward an arm would yield over the remaining time, assuming it's played continuously from now on. This simple shift in perspective enables a powerful insight. The optimal policy isn't static, it evolves with time. At every step, the best arm to play depends on how much time remains. CURE-UCB captures this dynamic by computing a horizon adaptive index that balances three key components. 1. Recent average reward, what the arm is doing right now. 2. Expected future gain, the average incremental value it will add over the remaining horizon, assuming linear growth. 3. Exploration bonus, a larger-than-usual term to encourage exploration in a rising environment where uncertainty grows with time. This index allows CURE-UCB to intelligently switch between exploitation and investment. When time is short, it focuses on high immediate returns. When time is long, it bets on arms with high potential, exactly what the optimal policy demands. And the theory backs this up. In structured environments like linear then flat instances, where arms grow linearly until they saturate, we prove a strict dominance result. CURE-UCB always achieves lower regret than horizon-agnostic baselines like R-ed-UCB. Why? Because R-ed-UCB, lacking knowledge of the horizon, keeps switching to new arms whenever it sees a high growth rate, no matter how short the remaining time. It fails to recognize that it might not have enough time to recover the initial performance deficit. CURE-UCB, by contrast, checks whether the future gain justifies the cost, and only switches when it makes sense. Beyond structured settings, we derive a general regret upper bound for concave rising environments. The bound shows that CURE-UCB maintains a favorable convergence rate, proving that its cumulative estimation approach is not just intuitive, but theoretically sound. We validate these findings through extensive experiments across synthetic benchmarks and real-world tasks. In the linear then flat setting, CURE-UCB consistently outperforms all baselines, R-ed-UCB, SW-UCB, T-UCB, ET-SWGTS, across all horizons. It achieves the lowest cumulative regret and maintains the best average rank, even in noisy, mixed scenarios. In the concave setting, where growth is nonlinear and more realistic, CURE-UCB again dominates. While non-stationary algorithms like SW-UCB fail to detect the late bloomer and R-ed-UCB overexplores saturated arms, CURE-UCB adapts perfectly, achieving near-optimal performance. And in a real-world application, online model selection on the IMDb sentiment dataset, where training curves are noisy and volatile, CURE-UCB performs competitively with the strongest baseline, R-ed-UCB. At a horizon of 50,000 steps, its regret aligns with the lower confidence bound of R-ed-UCB, demonstrating robustness in high-variance environments. So what does this mean? It means that knowing the horizon is not just a technical detail, it's a strategic advantage. In practical domains like hyperparameter tuning, robotics, or large-scale model training, where budgets are finite and well-defined, horizon-aware algorithms like CURE-UCB can dramatically improve efficiency. They prevent wasteful exploration, avoid premature switching, and dynamically align with the true optimal policy at every step. This work isn't just theoretical. It's a call to rethink how we design bandit algorithms for real-world applications. The future of adaptive decision-making lies not in blind growth tracking, but in strategic foresight, in understanding not just what's working now, but what will work in the future, given the time you have. CURE-UCB is a step toward that future, where algorithms don't just react to data, but reason about time, potential, and the cost of delay. And in a world where every training epoch, every GPU hour, every decision counts, this kind of intelligence isn't just useful. It's essential.